part, and then we will go back to the animation that we have seen, that we saw on the first lecture. Why should we study this system here? Because it's the simplest way to transfer energy in space, coupling. And it's a very simple version of, for example, the molecular forces that are keeping together this table, or weaker, the molecular forces that are taking together a pot of water, or, and they are still weaker, the interatomic forces, intermolecular forces that are keeping together the gas in this room that we can breathe. So let's be a very simple example, the spring. Now, what I'm going to do here is to study the simplest version of coupling between harmonic oscillators. And as we discussed 2 days ago, the coupling is decided by the constant of a spring. Let's imagine it is infinite. Well, we're getting nothing new here, because actually this will be a simple harmonic oscillator with a double mass. It has to go together. And this is very similar to the approximation that we take when we consider a fluid as incompressible. You move one part, immediately everything is moving. The other extreme is that the spring is not there. Well, we have two independent harmonic oscillators with their own energy. They cannot communicate. In the middle, the spring will mediate the transfer of energy. How fast? Well, it depends on the constant. 0 time, it's rigid. Infinite time, it's not there. So, now we are going to study a 2 degrees of freedom system, and we will discover that this system will have 2 conditions, and just 2, for which all the points of the system, 2, are oscillating with the same amplitude and with the same frequency. We will call them the normal modes of the system. What is important is that whenever the system can be described in a linear way like this one, the normal modes of the system will be an orthonormal complete base of this system, if you want to take the point of view of differential operators. What does it mean? We can build whatever solution in this system as a linear combination of the normal modes. The system can be a table, a room, a building, the earth. Of course, the number of degrees of freedom is increasing, going up to infinite. Yes?
Please, what do you mean by degrees of freedom?
Oh, that's a very basic physics question. Okay, let's take this as a single object. This can be moving in space in 3 directions. Okay? And you can discover, let's imagine the mass, like this one, just one. Okay? Since it is a point, the mass, you can imagine it's concentrated in a point, it can move in 3 directions, and its fate, its destiny, is decided by initial position and initial velocity. Dynamics are ruled by Newton's second law. We're in classical mechanics. Now let's imagine that you have another one, so without the spring. Still, if it is uncoupled, it's a single degree of freedom system. It has just one particle. Now, if you couple them, now the number of combinations that you can get, if they are uncoupled, they are 2 1 degree of freedom systems. If they are rigid, one destiny is deciding the other one. So it's still 1 degree of freedom system. Its trajectory in the phase space, if you want to take a more sophisticated terminology, it's still decided by 3 components of displacement and velocity. If you take 2 and they are coupled but not rigidly, well, each of them they can move in three directions, but there is one additional condition, that they are coupled. So if you want to write the equations of motion, it should be 3 plus 3 minus something. It depends on the coupling condition. If it is rigid, it's 3 plus 3 minus 3. 3. If they are free, it's 3 plus 3, 6. If they are coupled, it's 3 plus 3 minus, depends, 1, for example. Okay? But still you have 2 point masses. So 2 degrees of freedom. Let's imagine we had another one. It's a 3 degrees of freedom system. 4, 5, 6. If they're all uncoupled, it will be an nth set of 1 degree of freedom system. If they are rigidly coupled, it will be a 1 degree of freedom system with n masses, because you are moving them together. Now let's imagine this table is rigid. If I move one part, all the table will have to move in the same fashion. Actually, it's strong but not rigid. So if I knock it, part of the molecules will move later with some perturbation, that is a wave. Okay? Let's take another example. Let me go back, I hope it's here. We will use this couple of oscillators. Okay. Number of loads. Let me slow it. Are you able to see it? The resolution? Okay. Look, how many coordinates do you need to describe this system here? 3. Well, actually, 1. Because it's confined to one dimension. But, okay, let's use our fantasy. Maybe it can move in 3 directions. But now it's just 1. Now let's imagine to add another one. Now we have 2 coordinates that we need to use. If they are free, they are totally independent. But if they are coupled, let's imagine that you have a small spring there. They can move in different fashion. For example, I can plug 1 and something like that. So it's 3 plus 3 minus the conditions that are coupled. I can increase the number. 4, 5, 6, 7, and okay? Now we have n masses with n minus 1 coupling conditions. At the end of this small set of slides, you will see, I hope, 2 slides that are the beginning of a solid state physics course. Just to see, just to show that what we're discussing now actually can lead to lattice vibrations. But if you want to be more sophisticated, phonons. That will be your first official homework, but not today. So you can relax. Okay. Another version, simpler one. I updated the link. Where is it? And it is really what we're going to study now. It's this that we already discussed, if you remember. Okay? You see the time histories? Energy is plugged in one point of the system. Potential, if I move it. Kinetic, then energy is transferred. Then, okay, the universe is finishing there. So it has to come back, and to come back. You see now that the time histories under, yes? Yes? Try not to be late.
I think this is what
Pardon?
the
Okay, well, you studied the phase space, space-time. Okay, space is here, time was correct with me, but try to put space and time together. Okay. Okay, what about the two time histories that are describing these 2 degrees of freedom system? You see that one is getting, let's start it again. Okay, the red one will start with some potential energy. then that potential energy will go to kinetic potential. But thanks to the spring, the energy will flow on the other side, and vice versa. Okay, look at the time delay between the maximum here and the maximum here. The time delay is decided by the strength of the spring. If you imagine that the spring is rigid, there is no delay, and the two time series will be exactly the same forever, whatever condition you apply. If no spring, this one will be the time history purely periodic, not with maxima and minima, and the other one will be flat. So, the difference between these two is due to the coupling. And the coupling will decide how fast will be the transfer of energy between 2 points in space. Now energy is flowing in space. Okay? So, looking at that again, you will have something like that. Now, question, unpolite question, as usual, I'm unpolite and lazy. Have you ever seen, now let's forget the two pendulum. You remember in your relatively short career some pictures similar to this? I bet that you saw it sometime in the past. Have you ever studied beats? We're going to study beats for just 2 slides, maybe on Friday, maybe on the next week. What are beats? Do you remember? We are going to study them very quickly. It's when you sum 2 harmonic waves with slightly different frequency, and you have amplitude modulation. Have you ever? AM. You remember something? And the typical plot is that maxima and minima are appearing. Usually they are used in sound. 1, 1, 1, 1, 1. Okay? Sorry for. Okay. The plot is very similar. Now there is a connection between this plot and the plot of beats. I will let you, you're free, your spare time to think about it before the lecture that we're going to take. There is a connection. Okay, by the way, it's time to go to the boring part. The boring part is my PDF. We can skip the first one. And now we have to study the dynamics of this very simple system here. The PDF is online, I hope. Let me check. Let's check if the update has been working. This is seismology, but that should be working. Let me go to wave physics. Okay, should be this one. Okay, so that's the website that I was pointing to you. And if you open now the syllabus, I hope it contains the topics that we are going to cover. And at the end of it, these are the books that I'm going to mention to it. You know this. Thank you. Okay. We are going to use mainly this in the second part of the course. And I updated here let's see if it is working. Yes, one is working. Fast start. No. Oh God. I did something wrong yesterday. Why this is, okay, yes, it's working. Okay? So this is the updated version of. And then there is the Dr. Russell one. Uh-oh. This is not, oh yes. Remember, today is our target, and our climbing route is to study this. You see many oscillators here. How many? In this room? Well, a lot. But we're going to study, I hope, within today, this animation here. So let's move. Now, let's consider these two pendula. Let's imagine that now we take both and we move with the same amount on the same side, what's going to happen? Well, potential energy, in this case it's gravitational energy. So we know the pendulum, we know that for lazy people and small angles, how much is small? As a first answer. Then you can be more accurate. It depends on the accuracy of the experiment that you want to play. But we're lazy, so let's stay within 10. So it's linear, and we know that, of course, the restoring force is giving a natural frequency that is dependent upon g and the length. Full stop. Now, during these dynamics, the spring will not act. So they will move together with the same frequency and the same amplitude. There is no damping. Everything is pure here. Okay? Very nice. It's a cosine. Initial conditions, please remember. Who is deciding the amplitude? C.
Yeah.
Who is deciding? G and L are deciding omega 0. The system. Once you build the system, natural frequency is given. But initial conditions will decide the phase and the amplitude. So phase here is 0, in the sense if you use a cosine, because we're starting with an initial displacement. The amplitude that we give is deciding C. It's the amplitude. Okay? So this is very boring. Just two pendula that are moving together with the same frequency and the same time history. If you want, it's this. Oh God, too many things now.
So what is the effect of the spring on the degree of freedom?
No, wait. It's there forever, so 3 plus 3 minus 1. Or if you're moving in one direction, it's 1 plus 1 minus 1. But wait, in this condition, the spring is passive. Just in this one. Why? Because we're not exciting it. Because we decided to move it of the same amount on the same side. So it's working like that. They are in phase, same amplitude, same time history. Look, if I decided to move it not by 10 but by minus 9, the situation is a little bit different. You see that now it's not the same amplitude. So now the spring is weakly acting, but it's there. The spring is always there. The initial conditions will decide which kind of motion is going to happen. Okay? We're not doing rocket science here. Please, don't imagine difficult things. It's very simple. Okay. Now, whenever all the points of the system are moving with the same time history, with the same frequency, with the same amplitude, then if we put a label on that, it's a normal mode. My name is Fabio, that name is normal mode. The next one. Now we take the two masses and we separate them by the same amount but on opposite side. Now it's time for the spring to act at its most. The restoring force at any time will be the largest one. And if you want to write them, now the equations will contain the coupling. It's just Newton's law. What we discussed on Monday, plus this. Now it's an additional restoring force. Now if the restoring force is larger, the frequency of the oscillation will be different and it will be higher. Because it's like to have an additional restoring force at any time. So the frequency of this second normal mode, it will be different and higher. Now you can rewrite it. And now you see, this is the same equation of a simple harmonic oscillator in motion, but with an additional term. It's the coupling. Okay? Okay, let's go back to the usual. Infinite K, well, it's disappearing. because it's rigid. Omega 0 will not be important. Okay, you solve it, you call it omega prime, and you will have another simple harmonic motion, but with a different frequency. And the solution will be, one, it will be with this amplitude and new omega prime. The other one will be same amplitude, same frequency, but opposite phase. Okay, let's look at it. Same amplitude, same frequency, but opposite phase. Now you can play whatever, but these are the only two conditions for which all of the points of the system are oscillating with the same amplitude and same frequency. Just two. 2 degrees of freedom, 2 normal modes. 3 degrees of freedoms, 3 normal modes, and so on.
At this point, can they be described as standing waves?
Waves? Who has been speaking about waves?
I mean, can they be described as standing?
You have to wait. Maybe yes, but that will be part of your homework. But you have to wait. You know, it's the birth of a standing wave. But first we have to give birth to waves, then to progressive waves, then to standing waves, but I would say yes. But no waves up to now. Okay, now, since the system is linear and it has 2 degrees of freedoms, you can show, formally, I cannot, that the base, orthonormal and complete base of the system is given by the two modes. Does it mean that whatever strange things you want to play, let's keep -10 and 5 here, whatever, they can be described by a linear combination of those two. Now you see, the amplitude is not the same. Changing, why? Because the energy is going to be transferred in some time. Depends on the initial conditions. But the system is still the same. Now, what to do next? But now we are at the point where the second slide of my 0 lecture is reached. So we have been coupling two harmonic oscillators in an active way. Passive coupling like rigid is giving nothing. But a spring with not infinite constant, with no zero constant, is letting energy to be transferred in space with a given time rate. Okay? It will become wave velocity, but not yet. What's next? Well, that's a boring part. We can imagine now to consider 3, 4, 5, and coupled oscillators. Now you see this picture here where you have a distribution of n masses connected by some tiny elastic string, you can imagine like springs. And with some beginning of a universe and end of a universe can give birth to what will become a string. Actually, this is a string, but with discrete masses. Now let's imagine to stay so far from this necklace that we are not able to see the pearls. We will see it just a continuous distribution of mass. So going towards continuum mechanics. But why it's useful to consider this one? Well, because on one side of this bifurcation, we can go to lattice vibrations. Really. Now let's do it in a smooth way. And now let me use Dr. Russell animation. There should be one that is hanging chain, membrane torsion. These are too complicated for today. What is it? Wait just a second. Okay. Another multi-degree mass. That's the end. I think, Dr. Russell. Okay, we can use this one. One DOF, 1 degree of freedom system. We did it. Okay? 2. We did it. We've just done it. Now you can imagine one spring, and one in the middle. In this configuration, the middle spring is not working. In this configuration is working at its best. Here you have a combination. You can do whatever. Now the idea is to go on 3 degree of freedom. You can guess that there will be 3 normal modes. All the masses on one side and the 2 internal springs are not working. Then 2 on different sides and 1 is there. You see, this will never move. And the last one is this, a continuous phase change. You can do the same with 4. Well, we have no time to make discrete 7, 4, 5, 6, 7. But the idea is that one. And the next idea, let me find it. Where is it? Where is it? Where is it? Where is it? Because I want to... Okay, maybe it's here. This is what we're going to study today, I hope. And when we distribute the mass in a continuous way between one point in space and the other one, we can build a string. And now my question is, how many modes, normal modes, we have in a spring? Well, since we have a continuous distribution of mass, we can imagine to wiggle it in how many ways we can imagine. So we have an infinite set of modes. Why? Because the mass is continuously distributed. And we are going to call it the first, the second, the third, the fourth, and so on. Now the Earth is a 3D spherical heterogeneous version of this. But the principle is the same. Okay. Now, you can call this standing waves, but it's too early because I want to go there by steps. Now, let's consider this system here, and this will be the most boring part for today. What can we do with this? Well, leave it here and let's go to the seashore. No. We can imagine to perturb it. And now we can imagine to perturb it in several ways, essentially 2. One way is to move the pearls in a transverse way, like when you pluck the string of a guitar. Or the other possibility will be to move them along the axis. Those 2 ways will become transverse and longitudinal waves. Okay? Mechanically here there is no distinction, but one will go toward compressions and rarefactions, the other one will go towards lateral extensions. Still, the elastic spring will react. On one side, we will go at the end of the story towards shear waves in a solid. On the other side, we will go through sound waves, compression and rarefactions, and P waves in solids. That's the end of a tour. Now, what to do? Let's consider the simplest configuration. All the masses are the same. All the masses at the equilibrium are equally spaced. All the small, tiny springs that are between the masses are the same. And this discrete string is starting at one point and ending at another point. So these 2 black dots. These 2 black dots will become boundary conditions. Okay? So please remember, whenever you deal with the system, you have to write its dynamics, like for harmonic oscillator, Hooke's and Newton laws. And then, if it is 1D, initial conditions. If you have more than one harmonic oscillator, you have to deal with what's happened before and after, not only in time but also in space. That's a boundary condition. And you can say, well, it's rigid, I keep it. Or the other extreme will be, it will be free. But wait a second, because free does not mean free whatever, but it will be no force. The first case will be zero displacement, it's fixed. The other one will be, okay, free to flow without any force there. Just let me tell you that the surface of the Earth, usually, and also of the fluid, is supposed to be a free surface. No stresses have to be there, vertical stresses. And the system will try to go back to the equilibrium to keep it free. Exactly as when you throw a stone in a pond. It will react trying to put the surface back to the free condition again. So boundary conditions will contain dynamics, especially in fluids. Okay, now let's consider this. It will be the beginning of the wave equation in a string. And that's a really boring part now. Really boring. Now, let's imagine that we consider one mass and we pluck it in some way. Now, when we pluck it, we add some potential energy because we're making work against the springs, actually, or the tiny strings that are connecting the masses. If the masses are free, we move one, no reaction. Okay? It's not a set of free particles. Good. What's going to happen there? Well, we are creating angles. But wait a second. Okay, this is a discrete. No, this is a bar. But now it is a discrete set of masses. It's not, but okay. Now let's imagine that I move it. I don't care. I rotate it. You're not going to play a guitar just moving the guitar. Okay, you can crash it. The real perturbation that you want to apply is something like that, that is creating different angles in the different parts. We're not just applying a translation or a rotation. Okay? That's why when you pluck the system here, you're creating different angles in different parts of the system. So not just a pure translation or rotation. Good. What's going to change? Well, the length between the masses. In two directions, if you apply transverse perturbation, you will have a small perturbation along horizontal length, and most importantly, a variation in the vertical one. For lazy people, the cosine of these angles, if the angle is small enough, so you're not going to crash it, okay? I don't want to crash it. Well, it's plastic, so I could do that. You don't want to break the guitar, so they're very gentle. The horizontal variation will be so small that actually can be negligible because it's dependent upon the cosine. And for lazy people, cosine of a small angle is 1. The sine is not, as we know. Okay, so L prime can be imagined as an L and this vertical variation. But for small angles, and if you neglect the second order term in the cosine expression, it's small, can be ignored. It's quadratic. Okay, what about the vertical one? Well, now let's go to the P mass, and we know that it is coupled with the previous and the next one. That will be the real restoring force. Let's try to compute it for small displacements. The resultant force on any mass, for example, it will depend on the position on the other two. If the position is just a translation, there will be no change, because all the angles will be the same. Okay? Good. T is the tension that we imagine to apply to this necklace. This bar has already a predefined tension by its stiffness. We don't have to play like the string of a guitar with keys. It has already a tension. So if I perturb it, it's trying to go back. Okay? Good. Now, the boring part. Let's consider the sign of the two angles, because they will decide the restoring vertical force. You can write it, and for small angles, what's coming out is that the force on the fifth particle is nothing else than this. Depends on the tension that is inside, no tension, no reaction. It will be a set of three particles. The initial length, and then the relative position of each particle compared to the other one, for small perturbations. Now, that's the force. Let's ask to Sir Isaac Newton what to do with this. Well, you will get the mass and an acceleration. Okay? For the fifth particle, you write it, and you have a differential equation for that particle that, please notice, it depends on the position on the nearest ones. Good. You can rearrange it. I hope you trust that if you do the proper units computation, omega 0 will be a pulsation, so an angular frequency, angular velocity, so it will be 2 pi over f. Good. And that's the dynamic equation for that particle. Well, we're going to make a check. But you can write this equation for all the particles of the system. Please remember that the first particle, when p is equal 1, on the left, sorry, let me follow your system of vision, on the left will be 0, because nothing is there and you have a fixed point. Then you go, you go, you go. The last one will have a fixed point on the right. Boundary conditions. So in summary, what we can do, we can write a set of differential equations. How many? It depends on the number of masses. That can be solved by a computer, for example, from a numerical point of view. You have 1000, please do it. That's actually solid-state physics solved in a computational way. And then you can solve with the iterations, applying the first condition and the last one. Fixed, fixed, or free, free, or you can join them. So, actually, what we have written here, but we don't know, is a finite difference version of the wave equation. You will see in the next set of slides. What is funny is that now we are building wave equation from finite differences. Usually, when you have a wave equation problem, and it is too complicated, you're going to solve it by finite differences. We're making the tour on the other side, okay? So from finite differences towards wave equation. And these are called boundary conditions. Let's make a check. What if n is equal to 1? Well, we have to write just one equation. And it is this one. What about the previous, the two neighbors? Well, they are fixed points, so they are 0. Nothing, they are fixed. And so we go back to the equation of a simple harmonic oscillator, as it should be. Nice. And that's the frequency. You can imagine this. We did it. What if n is equal to 2? Okay. Now we have to write two equations. What about the y0 and y3? They are fixed. So, actually, you will get two solutions for which, and just two, for which all the points of the system will oscillate with the same frequency and the same amplitude. One is this, together, and the other is this one, on opposite sides. All the other possibilities are a linear combination of these two. Okay, and we can do this for n particles. Do we need that? No. Well, actually, I want to end this part with 2 slides that are the beginning of the solid state course physics. Just to show to you that we're not treating purely silly systems. For example, you can consider, and we are going back to this when we are going to discuss very briefly about phonons, and that will be your first homework. So, just a warning, a very friendly warning. And let's deal with our necklace with a very nice and hype name, monatomic 1D lattice. You could say, what is this? This is our system, classical system with springs. Yes. Now, the same necklace, if you want, with just different names. You can call them atoms. Good. What about the forces between atoms? Well, we can use a sort of a Lennard-Jones potential. All the masses are the same, and at the equilibrium have a given distance. How it is decided? Well, you put together the 2 potentials and you have this. That's an equilibrium. That's a potential. So you can write that potential using a Taylor series. So the value at the minimum, the derivative at the minimum, but wait, it's a minimum, so it's 0, and this term here. Then additional terms that will modify the parabolic curve trying to fit better that curve. But if you stay near to the minimum, it's a parabola. So we can take this. And you can call that a parabolic potential. Now, if you have a parabolic potential and you compute the force, you will get Hooke's law. Okay, it's called harmonic approximation, and what you have now is what we studied, that's Hooke's law. And now we have a set of masses with springs, keeping them together. What are the springs? Representation of the harmonic potential, interatomic harmonic potential. What should you do? Well, you have n masses, you have to write n equations of motion. And you have to solve them. The force is given by the springs. Okay, so what we did today, up to now, was to consider a monatomic 1D lattice. Do you like it? I hope so, because we will go back to this in a few lectures, and we'll discuss about phonons. Now, I think I've hidden them, but you have to know, oh no, look at this. We're going to study them. You like these vibrations here? Well, come on. The first one is nothing else than longitudinal, so with compressed springs whatsoever. The other one is transverse. Well, if you want to be hype and cool, you can call them acoustic longitudinal mode. The other one, acoustic transverse. You put 2 different masses, you can call them optical. We're going back to this. But please notice that this is nothing else than what we studied. Okay? Now, and I hope that now you can appreciate not this one, but what is it? Not this one, this one. Because now we can write the solutions for this one.
Sorry. So the image you showed or the animation you showed before.
Well, this one.
These are just corporate systems that we studied before, and corporate system.
Okay, look, we're going back to this. I want just to show to you how solid state physics animations, I was grabbing this from solid state physics. Actually, let's give a look just to the first 2. Okay? We can write a program to make this animation just considering masses and springs, and you add energy to one point of this system. you can imagine to do that, pushing one mass, okay, compressions. And the other one, you can imagine to pull it in a transverse fashion. Okay? So forget about now the names. I don't know how to hide them. Let me do something very brutal. I will not save, I hope. Now forget also the title. Okay. This is exactly what we studied.
Well, instead of springs connecting them, we just
You don't see the springs, but you have to imagine them, okay? They are interatomic forces. Otherwise, if they are free, and if I move one, the other will not move. It's like to put a set of pendula without springs. Or, if you put those springs, and they are so strong that they are rigid, as soon as I push one, I will push together all of them. Okay?
Yes.
So, or like that. But if I apply properly some perturbation, I'm going to play it. Now, let's hope that I'm not doing this. Okay. And the animation, the related animation is this. Just, we started from one, first two lectures. The first two lectures are also taking care about damping. It's there. Strongly damped, weakly damped, but not so weakly. No damping, I hope. I don't know if it is working. It will oscillate forever. Okay? What about today? We added two. We added another one, 4, 5, 6, 7, 8, and now we have to imagine to add an infinite number. No better. We have to imagine that now our lens is not able to see the distances between atoms. So we can imagine a continuous distribution of mass. I don't see holes here. When we walk on the pavement, we don't see the holes, right? Okay. In a more sophisticated fashion, we will see that our wavelengths will be much larger than interatomic distances. That's continuum mechanics. And to do that, the next is a boring part. Here it is. We did it. And now we take the same necklace, but we can call it a piece of a string. Going back to high school physics, okay? And we're going to find for the first time a wave equation in a string. So now we take this, actually better, a string, so we take a piece of a whatever, string instrument, we apply a tension, we don't leave it there, but we play it, we plug it in some place. Okay, good. That's a piece, that's a segment on the string. And now for the first time we can introduce density, amount of mass per unit of length. Why length? Because it's a 1D system. Now we are going to forget about the section. It's an ideal 1D system. So we consider linear density as the amount of mass per unit of length. Kilograms over meter. Okay? Good. What we should do? There is some tension applied to the string, otherwise it's not going to react. We call it F, and we are perturbing it in a way that we are creating angles between one side of the segment and the other one. No rocket science. If θ1 and θ2 are the same, we are doing nothing. We're just translating it. So we are plucking it. Okay? Good. Lazy teacher, that's me, small perturbations. Otherwise, non-linearity will enter there. What should we do? Look for forces. Now, forces acting on that segment is the difference between the tension there and at the other side. So, it's related to the difference between the signs. If no difference, no force. Just translation. Good. You can imagine what we should do now. You would say, okay, let's imagine that the angle is small so that the sine is like the angle. No. Or yes. But we will also imagine that the tangent, that is the ratio between the sine and the cosine, is practically the sine, is practically the angle. Why the tangent? We will see. Can you guess why? Look, when the angle is small, the sine is the angle, and cosine is 1. So the tangent is like the sine and like the angle. Very lazy. Okay, so now the total force is related to the difference between the tangents. Why do we need this? Well, because the tangent of an angle has an important differential meaning. It's the slope. If you take a function and you want to compute the derivative, well, the derivative in a point of a function will depend upon the tangent of the angle. And derivatives, now, we can apply them to the space. That's why we need it. Okay. So at the two sides of the segment, in A and B, the tangent has a meaning. It's the value of a derivative of a function at both points. Now what is that function? It's y. Wait a second, because now for the first time we have two independent variables. And that's why partial differentiation is there. At the time of the harmonic oscillator, we had just one independent variable, it's time. While space is just describing the position of the oscillator around its equilibrium point. With coupled oscillators, we have n equations describing the position of the oscillators compared to the equilibrium points. Now, space is describing where we are on the string. What is y? Y, as a function of x of t, will be the position of the different points of the string compared to the equilibrium. It will be the wave function. Still, we cannot call it wave function, but it's going to be. So please note one important thing here. The force at any point of a string is dependent upon the derivative, spatial derivative of the perturbation, that is y. Okay, so what? Well, now the total force applied to that segment can be written as the tension that is constant in the string times the difference in the derivative. No difference, no force. Now, Sir Isaac Newton. So, if we have a net force, we will have an acceleration. Mass times acceleration. What about mass? It will be linear density times the length of a segment. Good. What about acceleration? Well, now, it's not a total derivative, because we have to say where we are along the string. So it's the partial derivative of y respect to time twice. So please notice that compared to the other very simple case that was a simple harmonic oscillator where space was fixed, now we have to describe where we are along the string. So please remember that now we have a y of x of t, and what it is saying, well, if we have a string, and here we have x, we have to specify where we are. So every time, if you decide a point, you have to specify that. Do you want to specify a time? Well, you're going to take a picture of a string at a given time. Now we can assume 2 points of view. To be seated in one point of a string and let the time evolve, and we will have a stringogram, okay? Or we can take a string and take a picture and we fix time. So space and time. And this is the perturbation. That's why Now we will have transverse velocity, that is a velocity of vibration. But to specify it, we have to say at some x. Okay, so that's the force. So dynamics will be ruled putting together these two terms. You do agree with me, right? I hope. What's next? Okay, let's take some ratios here. Okay, what about this part here? You recognize something? For not pure mathematicians, that is a derivative. Because I'm sure that you remember that when we have defined a long time ago derivatives, and you have a function, okay, let's take delta f over delta x, and let's take it to the limit. That's the derivative, right? For rude people like myself. So what is this? Well, that's a derivative. Of what? Of a first derivative. So it will become the second derivative. Of what? Of y respect to space. Now, that's a wave equation. Because now we are ruling that the perturbation that is y as a function of space and time will have to obey this. Wait a second. Let's give a look to the units. And now we're going to call it a linear wave equation. If you want to talk with a mathematician, you can say it's a parabolic partial differential equation of a second degree linear. But more simply, we can call it a wave equation in one dimension for strings. Now let's give a look to units here. What are the units of y? Okay, because y is telling how far is every point of a string around its equilibrium. What are the units of x? Good. What are the units of t? Okay, now what are the units of the ratio between mu and f? Because they have to match. So here we have y and y, fine. Here we have time squared, and here we have x squared. So to be, how to say, really polite from a physical point of view, f over mu square root has to be a velocity. That's why usually wave equation is written as 1 over v squared. It has to be a velocity. Now, that's not the velocity of vibration. Please remember this. That's velocity of vibration. That's another velocity. It's the velocity with which the perturbation will travel along the string. That's wave speed. And you know what? Usually I'm using t, here it is f. We've just discovered a very important law. It has a name. And the French is coming again. It's called Mersenne law. It's the velocity with which perturbation, transverse perturbation, traveling along a string. Many people think that Pythagoras found it. No. It was coming much later. It's not very old. Not old at all.
Sir, the previous slide,
Yes.
the ratio of mu to f, that's the linear density to that of the force, can be re-expressed as the inverse of the velocity. So can we...
Wait, I was running too fast. I was simply saying, look, if you give a look, that's a differential equation. PDE, partial differential equation, second order, you can call it parabolic. Hyperbolic, sorry, hyperbolic. And if you give a look to the units, y, t squared, x squared, this has to be a velocity in meters per second. This is what I'm saying. Remember that F, it's not a pure force, it's a force over unit of length. Mu is a mass per unit of length, so units now are velocity. This is what I was saying in a rough way, so thanks for asking me to repeat it. Now, wait a second. I will take a shortcut now. Because, yes, within today you will show the general solution of that equation. But for now, let's make a first rough attempt. We know what are plane harmonic waves. And we know in some way that they are solution of the wave equation. Let's try. So let's take something that is a function of space and time, that is purely harmonic. You know, you can guess from the shape of the equation that was in the previous slide. Now, the question was, do you remember the harmonic oscillator? Now, the question is, what is the function that if you compute 2 times the derivative, it's becoming itself? It has to be sine, cosine, exponential, right? Plus, and this has to be positive. What are the functions of x and t that if you apply derivatives, are staying together? Sine, cosines, and exponential. So we guess that. So using that guess, let's try what's happening if we consider an harmonic function, like a cosine or a sine, as a function of space and time. We will see what k and omega will be. But for now, we have just to be polite. Space, time, and something that is putting together things. Radians over length, radians over time. Okay, what's going to happen inside that equation? Well, we compute the derivatives. We compute the derivative. You see, 2 time derivatives are getting down elements, but leaving the function itself. So we put them together, and what we get? This relation. And now by units, we get this. And if you give a look to the units here, this has to be radians over meters, radians over time, you get immediately the velocity. And you can write that equation as a general form of linear wave equation. Wait a second, V is specified by the system. It's not the speed of light. It's the speed of mechanical waves transverse, we will call them transverse, in a string with a given tension and a given density, as any guitar player knows. As I was telling you, okay, that's a description. So larger the tension is, faster will be the perturbation. Less the density is, faster will be the perturbation. That's why in a typical Western guitar, we have 6 strings with mass that is diminishing from the mi is the rating of the E, F, I don't remember, but 6 strings with decreasing density, okay? But you can play a sitar with many, many more strings. In general, this is called Mersenne law. And it's not so old as Pythagoras, for example. It's not so old. And this is what he published. So again, some French scientist was here. And let's take another one. But, okay, up to now, we know we have arrived to the last slide of our 0 lecture. So now we have seen that if we consider harmonic oscillations, we damp them, we have damped them, we have forced them, but okay, it's not important for today. But if we couple harmonic oscillators, we let energy to flow in space. Energy, not mass. Because mass is always oscillating around the equilibrium positions. molecules, but energy is flowing. Then we considered a continuous distribution of oscillators. We could take spatial derivatives. With a discrete system, we cannot compute partial derivative in space. It's not continuous. You do understand this. And what we have found is the first example of what we can call wave equation. So perturbation of coupled oscillators that have an equilibrium position and are gently perturbed. Of course, you can break the guitar and that's the end of the story. That's not a wave. They have to obey this ordered law that we're going to call wave equation. And by units analysis, that v is a velocity. Please don't mix that velocity with this velocity. Still, this is a velocity. Space over time. But it's the velocity of vibration of each point of a string, in this case, around its equilibrium position. So velocity of vibration, velocity of propagation. Okay? On Friday, we will go deeper into this. But now, I want to start, in the last 15 minutes, the beginning of maybe one of the most important wave equations. That is sound wave equation. Now we're going to change the point of view. We don't consider a string, I know it's a bar, but we don't consider a string, 1D. Now we consider a volume of gas. And by gas we mean something that is containing many molecules that have a sort of a tiny interacting force between them. It's not a set of free particles, okay? But it's tiny. You can move within it, you can breathe it, you can compress it. And what we want to study is not wind. That's for climate science. You're going to study this into other courses. But we're going to consider perturbations that are fast and large enough that are not just so tiny that the molecules at a given temperature are moving. We will consider them at the beginning as static, but actually they're moving. They have temperature. They have some kinetic energy. But, so they have a sort of a mean free path. Well, our perturbation should be longer than the mean free path. Otherwise, we will simply move one particle and no perturbation will travel. So it has to be fast and large. Large compared to what? Wavelength, much larger than free mean paths. Okay. What is the equilibrium position? Well, for kinetic theory, if we want to study thermodynamics, it's a mess. We have a huge set of particles moving at a given temperature and at a given pressure. But our point of view will be the classical continuum mechanics point of view, as we have seen before. So here are some wordy statements about the positions. And since I'm lazy, today what we're going to consider are perturbations along one dimension of this gas. And we will imagine that the perturbation will be a plane waves, for lazy people. And so we're going to study this. And we're going to build the sound wave equation using 3 steps, like a stair. The staircase will be made by 3 steps. And the first step will be very simple. I'm trying to speak about this just by words, then we will see that. Step number 1. If I apply a displacement perturbation to an initial volume of gas, for example a compression, I will change locally the density. If I stretch it, I will change locally the density. I will increase it or diminish it. Okay. Step number 2. If we change locally the density, locally pressure will change. You know that pressure is a macroscopic manifestation of the presence of molecules. So locally pressure will go up and locally pressure will go down. Third step. If we have a pressure imbalance, we will have forces. And if we have forces, we will have acceleration, Sir Isaac Newton. if we join these three steps, the staircase will lead us to some wave equation. This is what I want to do today. And we will start again from this on Friday. So, oh, what's upstairs? I was deleting the title. Okay, very nice. Equilibrium position. It's a gas. And we're going to consider also a specific gas, for example, atmosphere, Earth atmosphere. Just here, maybe, we have a volume over our heads that is causing a pressure, standard local pressure, and a given density. That's the equilibrium position. If I'm not speaking, well, there is some noise here, but it will be in equilibrium, silence. Now, the initial equilibrium will be characterized by initial pressure and initial density. What I'm going to cause, unfortunately for you, will be a pressure imbalance and a density imbalance. We're going to quantify this. We will assume that this imbalance is small. Not small enough for you not to hear me, but small. It will be. Actually, some waves are very tiny compared to the initial pressure. Good. Step number 1. For hype people, you can call this continuity equation. But I'm simply calling it step number 1. If the gas is perturbed by compression or rarefactions, well, we will have density variations. Why? Well, let's consider a volume here, the initial volume. We are considering a segment of a gas, like a segment of a string, but a segment of a gas. We have a unitary section here, unitary section here, okay? That's a volume. The amount of mass that is there has to be conserved. We're in classical mechanics. No fluctuations between bosons or photons, something like that, okay? Now, let's imagine that we're applying a perturbation to this volume. Then we're going to apply a displacement to one side and to the other one. The perturbation is S. S will be applied on one side and on the other one. You can imagine that if that perturbation is the same, we're simply moving the gas. Nothing new is there. Okay, don't get scared now because, okay, wait, it's just continuity equation. The amount of mass that was before has to be the same amount of mass that we have after. We are considering a unitary section here and unitary section there. So mass is just density, and now this is a normal density, the amount of mass per cubic meters, times the length. This is the old density, and this is the new density. Now, I'm lazy. Since we're considering a small volume, delta x is small. So the displacement on the other side can be written using the Taylor's formula, and as you can imagine, I'm stopping to the first term. So this one is like this, plus the partial derivative of the displacement there. Very nice. The new density will be written like that. So if you develop this multiplication here, you will get 4 terms. But some of them are small, are quadratic. Let's wipe them out. Now if you compare this with this, you get something that is very simple and very intuitive, because you're left with this. Now let's think about it. Let's imagine that the displacement that I'm causing is a compression. If it is like a compression, the partial derivative is negative, because Vs there is less than Vs here. If it is negative, multiplied by a density, initial density, with the minus sign, it means that delta rho is positive. Actually, I'm squeezing, so locally density is increasing. Vice versa, if I'm stretching, delta rho will be smaller. Nice. It's linear, and we demonstrated that if we have a variation in displacement, we will have variation in density. Very simple. Now, if we have a variation in density, we will have a variation in pressure. Don't get scared about the next slide. Okay, that's easy. Okay, if this derivative is 0, no sound. I'm simply taking my box and moving it. Okay? It's not a sound. Step number 2. Density variations will cause pressure variations. Now, what is relating pressure to density? That's Nobel Prize. Actually, if you want to be hype, you can call that a constitutive relation. Now we don't know. Let's call it F. It's a function. Pressure is a function of density. The simplest one is ideal gas law. P times V is equal to nRT. We will apply that later, actually on Friday. Now it's late, I guess. Okay. So the pressure is a function of the density. And at the beginning, it will be just like that. But we have changed the density. How much the pressure will change? Don't get scared, it's easy. New pressure will be the initial one plus delta P. That's what we're going to call sound wave. We need delta P. Okay, it's F of rho. So it's F rho 0 plus delta rho. Lazy Taylor, the first. Good. Now, if you compare this is P0, you compare with that, we get some Nobel Prize expression like that. If delta rho is positive, delta P will be positive, and vice versa. What is relating these changes? Well, this strange K that is nothing else than the derivative of a function connecting pressure with density at the equilibrium. Now we don't care about that. We just call that. It will be a key quantity. Good. That's by definition. Third and final step. Now we have delta P. And we have delta P that are different in the medium. So we will have active forces between the medium. Good. Step number 3. Pressure variations will generate motion, ruled by Newton's law. Now, let's take, for example, two sides of this gas. We'll have a pressure here and a pressure here. What is the net force? That now is acting due to compression and rarefactions, not due to lateral transverse variation. Okay, let's compute it. Lazy people. Taylor's first term, and what we got here is this. Now what is P? Is the initial pressure plus what we want to know. Actually this is constant, so out of a derivative. And we got this. Now that's the active force. And it has to be equal to Newton's second law. So mass, that's a density, times the segment, times a unitary area, and that's acceleration. Every time that we deal with dynamics here, the second derivative respect to time will appear because that's acceleration. Now we got the third Nobel Prize expression. You could say, wow. Well, that's interesting because in 2 weeks we're going to find this expression for a much more complicated system that is a solid. So you should admire this expression for its elegance and its simplicity. Question to you, is that a wave equation? Okay, we have this, nice. But, wait a second, that's S, this is delta P. We should write delta P in terms of S. Yes, step number 2 and step number 1. Look, step number 2, delta P is proportional to delta rho. Good. Via K. But delta rho, thanks to step number 1, is proportional to this. And if you put them together, we have a wave equation. And if you check the units, this tiny innocent k, strange k, is the square root of the square of the velocity. And you can call that sound wave velocity. But wait a second. So that's it. What is k? Now it's time, and that will be the conclusion. Let me tell you, this clock is 5 minutes in advance. Okay, so we're still ready.
Patient? Patient.
Oh yes, sorry.
And the previous slide.
Oops.
Yeah, yeah. The next slide.
Okay.
Yes. From the term on the Newton's second law, we have the density times the displacement.
No.
But the
No. Density
Times.
0 times
the
length.
displacement.
It's length of a volume. It's not displacement. Displacement is s,
Yes.
and it should be times a unitary area, but we have cancelling because it's unitary. We are considering a very simple one: planes moving in one direction. I'm lazy, you know. Okay, that's not displacement. That's the segment of the volume. S is displacement. Okay? Now, final slides for today. And Newton is coming again. Can we guess something about the sound wave velocity? Now it's time to give a very quick and brief look to thermodynamics. For a guess, we need to specify some laws now, for which this perturbation is traveling. Well, you know, Sir Isaac Newton was always correct. Always. Except one case. This. He was guessing at the time that the passage of a perturbation like this, that we can call sound, was isothermal transformation. It was so fast that the system had no time to change temperature when this is passing. So he said, well, pressure times volume is constant. Good. This means that pressure over density is constant. We don't know that constant, but okay. Now V, remember what is that small k, is dP over d rho. Okay, that's a constant. Actually, it was wrong. Because the perturbation is traveling so fast in the medium, but actually what is carrying is a change of temperature. What the system has no time to exchange is energy. And so Laplace was coming just a few years later, but and also before, and the debate was won by Laplace. He was saying, wait a second, the process is adiabatic. So P times V to the gamma, and gamma is the ratio between the specific heats, is constant. There is a tiny difference. And the difference is that now you have a gamma. And you know, you have two mathematicians, physicists, that they were competing together. But at that time, the first experiments were done using light that was much faster than sound. So with lamps somewhere and cannonballs, something like cannon sounds, and they were measuring the speed of sound. And Laplace was correct. Because with gamma there, sound is a little bit faster for an adiabatic process than for an isothermal. The end of a story, oh, it's not the end because actually we made many simplifications here, but this is the end, is to give an expression of this speed. And what we can do now is to look for a specific constitutive law between pressure and density. If you assume that, for example, the atmosphere or the gas that you're considering is ideal, then you have something that is relating all these quantities here. Ideal gas law. And now step number 2 is becoming clear. It's decided. It's for an ideal gas. Good. if you take this, and if you take the Laplace expression, and if you're rewriting many things here, you will see that you have many different ways to write the same expression here. But actually, the speed of sound depends on gamma, it's the ratio between the specific hits at constant pressure and constant volume, times a constant, times temperature, times the molecular weight of the gas that you're considering. Now let's consider the air on the Earth. As a very first and good approximation, it's a diatomic gas, N2O2. And so, gamma is 7/5. That was the factor that was modifying the speed from Laplace from that of Newton. And if you apply there the molecular weight of a typical Earth atmosphere composition, you will get that expression. So gamma is decided, molecular weight is decided, and that is the speed of sound. So nowadays, that is a relatively nice and warm day, it's about 342 meters per second. Do you think it's fast? Well, it's not that fast if you compare that with sound in solids. It's not that fast if you compare that with sound in water. Actually, we will see that there is another way to write that sound speed. And I don't remember if I put it here. Yes, final slide for today. Because, and this definition will be very important for solids, but also for liquids. There is one elastic parameter that can be called bulk modulus. Now it's quite simple. Let's imagine to take a sample of something, could be gas, could be water, could be stable here, and you apply a pressure to all the sides. And you measure what is the percentage of volume that is changing when you apply that pressure. Now, if you take a diamond, or something that is infinitely incompressible, you will get zero change of volume, whatever is your pressure. If you take air, it's easy to be compressed. So bulk modulus, that is called also uncompressibility modulus, is expressed like this, as the ratio between the pressure that you are applying over the relative change in volume. Infinitely rigid, well, that's zero, and that's infinite. Soft, this is going to be large, and the bulk modulus is becoming lower and lower. Well, actually, you can rewrite it as this. But wait a second, because if you go back, and if you look to the Laplace expression, the P over dV is exactly what we were looking for. And P is gamma times P. Now, that's another definition. But if you give a look to this, sound wave, oops, that was supposed to be. Sound wave expression can be written as the square root of something that is similar to Marcian's law. Now, instead of F, you put B. It's the bulk modulus. Instead of linear density, you put the normal density. And you take a square root. So you see how the sound speed can be written in terms of the ideal gas law, or using, if you want, the compressibility of a medium in terms of this. This is very nice. You know why? Because pretty much all the mechanical waves that we are going to treat, and S waves and B waves as well, will have a similar expression. Think about this. Numerator is containing the restoring force. Denominator is containing inertia, that is density. And it is similar to what we discussed 2 days ago. Restoring force, inertia. So, you see that's a shortcut to remember sound speed. But if you want to be more explicit, you have the other expression, where you immediately notice that once you fix the gas, once you fix the constitutive law, the speed of sound is decided and it's dependent upon temperature. Okay? So on colder days, its sound is slower. Okay, that's enough for today. What we did was to couple oscillators, so many that we don't see the distances between them. We have considered a continuous distribution of mass. We have written the dynamics for strings and sound. And now we have found wave equation and two velocities. What we are going to do on Friday was to explore, not this, but this animation. Because actually we have written the equations for this. So that's our task for Friday, to study this animation and to study wave functions. So the solutions of the wave equation. For today we derived the wave equation from scratch. Okay? Your homework is just to reread this part. Okay. Thank you and see you on Friday. Your witness is that I was pressing that button. And now I am pressing it again, but still is. Still it's blinking. I don't know. But I tried.
The lecture wasn't recorded.
No.
Again?
No. I was pressing the button, but usually it should be. It's blinking if I press.
Sorry.